of, about our work, named Model-Free End-to-End Learning of Agile Quadruped Locomotion over Challenging Terrain. First of all, let's see our simulation results. We can see this is a standard short gate, and it can climbing the steps very stably. And this is a rough terrain. We can see that it can recover very easily when it nearly falls down. Let's see the introduction. We made a 12 joints quadruped robot learn to walk in a standard short gate pattern and traverse various of terrains. And most of the works on reinforcement learning driven quadruped robots are based on a predefined model. They are difficult to train and contain complex models structures. And the main contributions of our work is that first, obtaining an easy training model-free methods of reinforcement learning to make the quadruped robot learn the standard short gait and traverse various terrains. And second, introducing the inverse kinematics to reduce the training difficulty. Let's see the coordinate system and leg structure of our model. We use Unitrace A1 robot. It contains 12 joints. Each leg contains 3 joints. They are hip, thigh, and calf. Thigh and calf are in the same length of 20 centimeters. And we choose the center of mass as the origin of coordinate system and use the Euler angles to represent the orientation of the body. And this figure represents the framework of our whole model. And we can see that at the frequency of 20 Hz, the environment returns the status information of the robot to the multi-layer perceptions, which is MLP. Inverse kinematics then converts the feet positions output by the MLP into the joint positions, expressed in radians. PT controller converts the joint positions into torques, and then environment returns the rewards. And PPO finally upgrades the policy once in a while. Although the MLP we used is 3 layers, which contains 400 and 200 and 100 hidden units, respectively. And the sensors we used are IMU and foot contact force sensor. They are also very easily available in the real world. The figure on the left explains how the standard short gait look like, and we can see that the key point is that to make sure the diagonal foot to be consistent. And the pictures on the right is that we restrict the action space to a small zone that 30 centimeters high and 24 centimeters wide. This is very useful to reduce the difficulty of training. And this is the most important part of our work. Reward functions. This line is total reward functions, and we can see the details in the paper. And also, the reset conditions is also important. Reset conditions means that when the robot faces a failure case, the reinforcement learning will start a new episode. And it contains the attitude angle, hit of body center, and the total motion time and body collision. And next, this page includes the main functions about our inverse kinematics method. It is given a coordinate of the foot. Inverse kinematics will give us the joint rotation angles. These formulas can be easily deduced. And the picture A represents the foot contact law when the speed of the robot less than the 0.7 meters per second, and the picture B represents foot contact law when the speed of the robot greater than the 0.7 meters per second. And the picture on the right is at the foot motion trajectory. And we can see that it's very smooth and natural.